So last time we talked about plane wave interference and how it depends on this phase factor delta. That was K1 minus K2 dot R plus the difference in the phases for each wave, epsilon 1 minus epsilon 2. So next we're going to look at a bunch of different physical situations and see how we apply this in a real experiment. Often what you do is you have a point where the waves are going to actually overlap and they take different paths to get there, and you have to figure out how much of a different delta do they build up. All right. So the first one we'll do is Young's double slit experiment. Very famous experiment and was critical to demonstrating that light behaves as a wave. So typically it's drawn like this, and you got a slit there and a slit there, and it's drawn like that. And here is Thomas Young, by the way, who helped show us that light is a wave. And he says, actually, oh yeah, there are 3 slits. We often call it the double slit experiment when there are actually 3 slits, and like this. So these are walls here, and there are the slits. And then he says, can't anyone count? He's sort of annoyed about this, and sure, Faraday can't. Okay, well, that's kind of a cheap shot on Faraday. But let's talk, before we get into the real math of the interference term, let's talk about why there are 3 slits here. It has to do with coherence, right? Why 3 slits? Coherence. So coherence is an issue of how waves behave in the real world as opposed to the artificial way we describe them. So if we have monochromatic light, basically having one frequency, we might describe it in some simple way as having some amplitude times sine of kx minus omega t. Okay? And that sine kx minus omega t goes on forever. It's a sinusoid, and if we plot it, it never stops. Whether I'm plotting versus space or time, it goes on forever. Well, real waves don't really do that. Real waves stop and start. So this is what real light might look like. So what you might imagine it doing, if we were to plot it, is say it's going off and it's a fine, nice little sinusoid, and then suddenly it skips in phase for some reason. And then it's going off as a nice sinusoid, and then it skips in phase again. And maybe even before you started, everything was fine, and it skips in phase again. So real light can't make a pure sinusoid for infinite time and infinite space because there's just not room. So what's really happening is you have a mixture of wavelengths, and it's a big complicated mess, and coherence theory is actually very, very difficult. So what we're going to do is just sort of point out little ideas from coherence theory and kind of use them to explain a few things we see. So if you take this simplistic view that real light or incoherent light is really just coherent wave trains that get interrupted, then you would say this little length of the wave here is the coherent part. So if you're thinking in terms of time, this is the coherence time. Or if you're thinking in terms of space, it's the coherence length. It just depends if I'm plotting versus x or versus t. You can look at it either way. But you can imagine it as a wave stays coherent just for a little bit. Okay? So if you're working with natural light, like Young used, the coherence time is about 2 nanoseconds or so. Okay? Not very long. You only get little short wave trains on a macroscopic scale, or on a macroscopic time scale, that remain coherent. So we'll see how that affects different aspects of his experiment.